My interest of course is in gain, and if I see a equivalent circuit of a normal amplifier using a MOS transistor, very low frequency circuit, nothing very great happens, and let us say it is a common source, and I figure it out that this is what is going to be seen by me. And this current source and this R0 somewhere related to the device. This is a small signal low frequency equivalent circuit of an amplifier, common source. We will come back to it again, I am just trying to say you. So my worry is, if in a circuit, if I have a current source which essentially I am showing you something like this. Now this current source is a function of GM, essentially means it has something to do with the device as well as the amount of biasing I am going to do with it. And since GM is what is most worrying me, I would like to have a model of a transistor which will replace or which will give me equivalent of GM expression, because at the end of the day I can only solve something numerical. So I must create a equivalent circuit for a current source in terms of device parameters, and once I know what those device parameters I have to govern which will control my GM and similarly R0, then I will say I have designed an amplifier for a gain of V0 by Vin, which you can see very clearly is if the gain is simple like this, it is minus GM R0 parallel RL divided by, there is no input impedance right now, so it is infinite there, so 1 upon infinite, so 0, there is nothing, 1 only appeared, 1 plus that. So obviously if I want to control gains, I must control GM and R0. Okay. If RL is very small compared to R0, I am not very keen about R0 either, but in normal case I may be interested to know what are the values of R0 and what are the values of GM, so that I can control V0 by Vin. That is my ultimate aim. Okay. Of course this is a simple circuit, we will actually modify the circuit more complex way, and we will see whether we can have some equivalent model of a transistor which represents equivalently of this circuit. Okay. Because at the end of the day when I design a chip, I have processes and I have sizes. Okay. You have done a MOS transistor theory earlier, so we know we can only control sizes, W by L's, we can control partially mobility which is not very much in my hand, which is technology dependent. So all that I will control is threshold and W by L. And of course power supply is also not in my hands, by technology node someone say okay 1.2 volt supply, that is the end of it. To some extent therefore control is only on the sizes and also on the threshold I adjust. So I want to create a model for GM, R0, many other things, so that I will be able to control GM and R0 so that I can attain a gain of my choice. That is the design. If I analyze, analysis is so straightforward, but I want to know, I want a gain of 10,000 for 10,000 and above means I do not mean how much, but 10,000 minimum I want. So what should I choose the values in a device, so that when I interconnect on the chip that all circuit, it will give me a gain at least 1000, 10,000 or maybe lower or higher, whichever value you choose. That is the difference between, I keep saying, between analysis and design. I now want to know this value. Now I figure it out that that is not so straightforward. If I control something, I will figure out something I may lose. So how to get optimal use or optimal parameters, so that I get whatever everyone is asking, I can attain to a great extent that values, and that is what the design is all about. Okay. So if I had to create a equivalent circuit or equivalent model for this, I must do something we have done in second year, but I will do little more detail here. That time you probably were not very receptive, at least many of you I know about. So now at least have a word again. so that you know that why these values are relevant for example threshold, how do we control a threshold? Okay. Sometimes that threshold control is beyond you, sometimes it is well within you. The same technique which I am using for analog threshold control can be used even in the case of digital circuit, where we may probably do what called low power circuits. So threshold control is a major area where we actually look for design. Okay. At times technology forces you to do only this much. Okay. Then circuit wise what do I do? If everything is fixed by technology, then what do I design? So there must be some circuit way of fooling a device, or vice versa we may say, so that we still have some leeway to design. Okay. So that is the aim of this course. We were looking for MOS transistors already, for this is all n channel device, and we say that if VGS is positive and substantially higher, okay, one can see from here it is going to say, let us say VDS is 0 and source is also grounded, substrate is also grounded. It is like a MOS capacitor which has the oxide thickness of Tox, which has a dielectric or permittivity of that dielectric is epsilon ox, and because we are applying VGS as we did last time, initially there will be a depletion charge because we want to balance charge put on the metal plate or gate plate, and this, since positive gate voltage is applied, you need negative charges to appear. So first thing the holes move away and you create a depletion there, and I said last time that this can continue infinitum because that depletion thickness can keep on increasing, but it does not occur because one figures out that at certain value of threshold VGS equal to VT, the electric field in the depletion layer is large enough so that the whole electrons which are constantly generated everywhere including depletion layer, they get separated in depletion layer because there is an electric field. Please remember Poisson's equation says d by dx is rho by epsilon. If there is no rho, so there is no, P is equal to n means no rho, so E is constant or 0. In most cases the neutral regions have electric field assumes 0, whereas in the depletion layer you have an electric field and that can separate electrons and holes. At the point where it occurs we say it is VGS is actually defined as threshold. Now this is what we said last time, and we said depletion layer width is proportional to the surface potential, that is drop in the semiconductor surface, and one can see it is inversely proportional to the doping in the substrate, whereas size itself is a function of any. Okay. Size, which is called Fermi potential, surface potential, twice of Fermi potential is given in this expression. So we say if I had 2 phi f, I have already term in any, in XD I have another term in any. Okay. So there is a transcendental equation, so for a given any you can get a good charge equivalent of this, you have to solve a quadratic kind of nonlinear terms. Okay. Now we defined further, I mean this is what we said last time, if we continue to increase VGS further above VT, we need more minus negative charges in the semiconductor, and now we say the depletion layer has already reached its maximum, and we said this occurs because now free electrons can be created, holes will still move down but electrons can come to the surface, which is called the inversion layer because it is opposite of the substrate which we started with. Not going into too details of MOS transistor, MOS capacitor theory, one can say VGS, which is now equal to VT when threshold starts, the turn on starts, it is 2 phi f, which is the maximum surface potential which we reach, which is twice the Fermi level, minus Fermi energy Q phi, minus Qs, which is semiconductor charge divided by Cox, and this as I said it stems from the very simple relationship. If you wish one can derive very fast, not very accurately, but psi s plus Vox is equal to VGS. Now we know D is epsilon SES, D is assuming the electric vector, and we assume right now, which is not very bad assumption, across the insulator and silicon D is continuous. This is slightly worrisome. Essentially I am saying epsilon ES is epsilon ox EOX. the EE for both is same, that is the continuity of D vector along the semiconductor to oxide. Once we assume this, we also know the charge in the semiconductor can be written as epsilon S. Capital E is the field and small e is the dielectric permittivity. So the charge is minus epsilon S ES, D is continuous, so I have one relation here and another relation here. Now I can say, oh, I can now start playing games. Okay, I say from here, this expression you can choose from here, I can write epsilon S ES is equal to epsilon ox by T ox. Okay. Now this term from T ox is coming from here because this E ox, oxide voltage whatever you are seeing, the field across this is nothing but voltage divided by the thickness. So this V ox by T ox is epsilon ox, okay, not epsilon, E ox. Okay. Now this epsilon ox by T ox by capacitor theory is the oxide capacitance per unit area. Okay. So this C ox is defined as oxide capacitance per unit area. So C ox into V ox is minus Qs, is that clear? Qs is by Gauss's law is minus epsilon S ES, so I just substitute here. So from here I get V ox is equal to minus Qs by C ox. So what did I do? That this expression in which I know at threshold how much is psi s? 2 phi f, that I know because it is only function of Na by N temperature, Na by Ni, ln of Na by Ni into kT by Q, twice of that is twice kT by Q. So I know psi s, I know now Vr, because if I know Qs which is the charge in the semiconductor, charge density, please remember this is all density per unit area, that is why this is per unit area, this is per unit area, so it is a voltage. So if I now have a term which is I know Qs directly otherwise, I know our C ox anyway because the oxide thickness has started with T ox. So I know how much oxide thickness I have and therefore I know the oxide capacitance, is that clear? So I know my V ox. Once I know my V ox, at Vt one can therefore say psi s is 2 phi f minus Qs by C ox at Vgs equal to Vt. This Qs at that time. So at how much is Qs at the when the inversion starts? Qna xd max, is that correct? Qna with a minus sign because the negative charge. So we say this, okay, so at threshold voltage therefore I have a 2 phi f term which is known to me, I can calculate, and this is minus for n channel minus Qna xd max by C ox. So one can see from here every term is known from the device. Doping concentration is known, from where you can calculate phi f. I know phi f, so I can calculate xd max because it is a function of Na and 2 phi f. So I can calculate the Qs by C ox term, I know 2 phi f, so I know my threshold. Okay, so my threshold, that is how I know threshold. Since this quantity is minus and the sign here is minus and 2 phi f, as I say band bending down, phi is positive, so both terms are positive adding to each other, which means threshold for n channel device is always positive. However, this statement can be modified little later, but that is what we want, threshold of an n channel device should be always positive. If it is 0 or negative, what does that mean? That the inversion has set in even at 0 bias, because threshold is lower, so by the time you reach 0 volt already inversion is already available, and that was one of the major worries in earlier technologies. We started with, as I said earlier, we started with P device circuits for simple reason, because gating the other two terms which I will show you now were so strongly negative that the Vt used to become net negative. And once that becomes, then that means device is always on, in terms of device called depletion mode, it is already in the depleted situation, okay, which means always on, okay. So you have to go minus higher voltage to switch it off. In a circuit we never wanted that to occur, we want on off, particularly for digital for example. So 0 to something it switch on. Now that was not possible. So we said okay, look for p channels. In p channel this is negative, this value will become plus q nd xd max. So this will minus sign will hold, this will be minus, the other two terms are always minus. So all the terms which you will get is minus Vt, but p channel I want a minus Vt. So if there were situation, those two terms which are minus only may add to minus value more. So to turn on a device you will require much higher minus voltage so that it crosses Vt. That was possible because okay, instead of 3 volt I may put 5 volt supply, 5 it doesn't I will put 10 volt supply, minus of that. However, if I have a minus Vt for a p n channel, then I have a problem that I cannot then turn it on at normal biases, and that is why I say we started with. So what are those two terms which caused so much worry for most of us? There are two assumptions we made so far. One is we said there are no charges in the oxide, which in reality they are. There are charges very close to the interface. Okay, they are normally always positive. Normally I will not go too detail on that. They are called fixed charges, and normally within 100 angstroms from the interface they are situated. Now take a situation in which you have a charge at the interface. What is the problem with us? If I have a device and this is my oxide and this is my semiconductor, let us say positive charge occurs very close to this is oxide and this is semiconductor. What it will do, I have not applied bias, but this positive charges itself will now expect negative charges to appear in semiconductor to balance the charge neutrality. That means anyway by VGS what we are going to create, negative charge. So even without VGS I have some charge already available. Is that clear to you? Already there are charges available to you. Similar thing happened if you have a metal. Okay, this is your metal. Our assumption is between metal and silicon the work functions are same. Okay, work functions means the energy taken for electron to leave the material is called its work function. We assume initially phi m is same as phi s, but in reality the material will have different phi m's. For example, if you put aluminum as the gate, aluminum has a 4.2 electron volts as phi m, where semiconductor is typically 5.2 minus phi s, phi f values will just around 5 eV for example. So it means phi ms, phi m minus phi s is negative quantity for aluminum. Even with the silicon gate which we use, poly gates as we say, the polarity of poly and the substrate will be opposite, so there will be again difference between phi m and phi s, which essentially means it is normally, and normally depends on the metal used or something you use, phi ms is always negative. That means if phi ms is negative it also wants something additional already available to you. Semiconductor is already having some negative charges already sitting there. We also have positive charge which also is already created this. So normally how do we measure? Equivalent level. So we say okay, apply additional as if this voltage so that the equilibrium is attained. Fermi level on both sides are equal. This is called flat band. Okay, and from there we now say inversion can be set in, but this additional voltage was already charges were available. That much you won't need now actually. This is already present with you without worry. Now the problem is this is giving you negative, both values on negative charges, and you are going to create some negative charges due to VGS, but these charges may be sufficient for the inversion to be there, which essentially means that the device is pre at 0 itself at an inversion. This essentially is the worry, which means the Vt of an n-channel transistor could be fully negative. Two terms were positive, but these next two terms which I will now show you may be strongly negative compared to these two positive terms, and here is that expression I am talking about. This is my 2 phi f QS Cox is what normal Vt would have been, but two assumptions I made, Qox is 0 which is not 0 and phi ms is 0 which is also not 0. So if I add those two terms without going into details of band diagrams, because some other day specific someone wants come to me, I will explain you MOS theory even much more in detail. So why we say that? Because that is our bread and MOS transistor we have been working for 25 years or 30 years, okay, or maybe more, 35 years. So for us it is very trivial to understand what is going on, but for you it may be interesting, some of you, not all of you. Vt is equal to phi ms plus 2 phi f minus qox by cox. This relation comes from the fact, you can see from here, why did I say total charge initially was 0, but if there are oxide charges, this is the new equation, charge neutrality. If that occurs, we can say Qm is minus Qs plus Qox, and this I call, since this is fixed, I call it Qs dash, okay, and then I substitute here Qs dash, okay, because that is a constant value. Qox is always fixed from the technology, positive, always known to me how much. If that is so, I will get additional term of minus Qox by Cox here, okay. Now this is negative, please remember in the expression this term is coming negative, this is positive, this is negative, this is positive because minus Qna, so this, but these two terms may offset these two positive terms. This has happened because initially when technology started in 60s, the Qox was extremely high in the process we made, okay. It was of the order of what we say 10 to power 12 per centimeter square as the density, multiplied by charge it will be coulomb per centimeter square. So it was a very high charge density was available in the interface. So whatever we do for n channel, it will always be on irrespective what we do. Now we figured out in 20 years, 15 years down then, that I can control Qox by technology details. I can do something which will reduce my Qox. Now I can do a Qox of 10 to power 10 per centimeter square into Q, of course, which means this term will be very small, and in which case this may not be strongly negative. Of course this I cannot play much, this is a inbuilt gate whatever I create, but this stronger term may become smaller and then the net value may become positive. Now one catch from all this, if I want to increase Vt with a given Qox and phi ms, what is the term I should improve on so that the Vt goes higher? That is the circuit requirement. From here expression, can you check what should I increase? Na, the doping in the substrate, if I enhance, I will be able to enhance the threshold voltage. That is the control, that word which I say control, I can do some technology control. Now I say okay, boost the Na, okay. It may have something else a problem, so I will okay selectively boost the Na wherever I want, that is in the channel only I have higher doping, substrate I do not have, which I can selectively dope the device, okay. So the way thresholds could be adjusted. Also you can have very interesting thing, you can have two areas or two separate transistors may have different dopings and we have a multiple Vts on the circuit itself. So tomorrow you design a good analog block or a digital block and you expect variable Vts, technologically it is called additional mask, okay. Extra one mask is typically cost around $1 million on process, okay. So you say one mask, $1 million, another Vt third you want, another mask for just for that, another $1 million, okay. Typically 24 masks are required for making a good chip at CMOS chip or an equivalent of a chip. Now you add this, as now new technologies are coming and many controls are being given, you may require 34 masks. So now remember how much money per mask you are adding, that adds to the chip cost, okay. So what Intel Pentium 4 initially was sold maybe $140, and now they may sell it $200 because now I have improved something which is multiple something I am giving you which can control your power requirements. So all technologies cost you on that. Of course if you make billions and trillions, that cost may actually go down, that is what the whole game in the circuits are, okay. So is that clear? So the basic idea of a MOS transistor Vt control is to control, alternatively you can also control it from Cox or Tox, but Tox is not very much in mind, it is a technology dependence. When you say okay 90 nanometers should have so much thickness of oxide, 0.25 should have so much, I mean that is the technology, so I am not very much within my this. But if I see C, there is an epsilon term going on. Oh, so I need not work on silicon dioxide, I may look for other dielectric with higher epsilons, okay, and in that case high K dielectrics actually came up, okay. Of course they have their own problems. So in general a typical capacitance voltage characteristics of a MOS capacitor looks something like this. This is for n channel device. What does, please remember, P substrate always gives you n channel device, n substrate will give you P channel device. So this is n channel device means P substrate device. So we apply, what is the threshold for P channel, n channel device? Positive. We assume right now that QOX and these are small enough, so they still shown VT. So if I have VGS negative, since there is an accumulation, you can see in accumulation there are plus charges and there is a metal charge, plus plus. So it is a good MIM capacitor, metal insulator, larger charges mean equivalent metal, so you have a metal insulator metal, okay. So fantastic capacitance came, okay. So you say COX is the only capacitance available when you are in accumulation. However, if I start increasing VGS towards positive, somewhere down I said as you cross 0, VGS becomes positive, depletion starts, the depletion layer starts and you start getting negative charges due to depletion. Now what can you see? You have already seen that figure, which is a capacitive figure. You can see from here, this is metal, this is this is metal, this is oxide, this is the inversion layer, and also there are acceptors here, okay. Now this has two capacitance now, one due to the oxide and one due to the semiconductor. Semiconductor charge means it is equivalent of a capacitance there, and you see they are in series. So what we say therefore, it is like saying you have a COX in series with CS, which is semiconductor capacitance. So after VGS becomes positive, there is a semiconductor capacitance which is essentially how much? Epsilon x by xt. This is Ks epsilon naught. Ks is the dielectric constant, epsilon 0 is free space permittivity. So this is, please remember epsilon is K silicon n to epsilon 0, silicon dielectric constant of silicon dioxide is 3.9, okay. So epsilon s is known to me because this is 8.854 10 to the power minus 14 farad per centimeter. So I know now this is series in compared to COX. What will happen if you have a series capacitance? The net capacitance seen between these two nodes will what will be? It will decrease, you are in series. As you increase VGS, XD increases, CS decreases. So what will happen to the net series? C further goes down, okay, C further goes down because CS is started going towards smaller value. As this reaches maximum, you will reach CS minimum, okay. Now you cannot have further depletion layers, okay, XD max has reached. Now the net capacitance is COX in series with CS minimum. Where this will occur, this XD max, when the threshold occurs. So if I keep increasing VGS, somewhere at VGS equal to VT, I reach CS minimum, so the net capacitance then becomes constant. Now this is slightly catch, I showed you two curves, one shows constant and the other shows it goes back to higher value of its original COX. This is essentially because of the frequency of measure. How do I measure a capacitance? I apply a current source or a voltage source through a resistor and pass current through a capacitor. So what is the current through a capacitor? C dV by dt is the current, or j omega C times V is the current in the capacitance. If I know my omega and I measure the impedance on an impedance bridge and I know what currents I am, voltage or current I am pushing, then I will be able to evaluate the capacitance, okay, assuming R's are practically 0. Once I know 0, but then that omega term appeared there. That means the frequency at which I am monitoring will give me the impedance. If omega is very small 2 pi f, then I am in a low frequency zone. If omega is megahertz, tens of megahertz or 1 megahertz and above, I say I am in high frequency range. Now why this at high frequency, what happens when I apply higher frequency? Basically what I am doing, I have a DC over which I am superposing AC. If the frequency of AC is this, whatever this capacitance here I was monitoring, I must say that the depletion charge must vary with the frequency, because you are going plus minus, okay. At much higher frequency depletion charge cannot follow that. Is that clear to you? So it shows constant value, but at very low frequencies it has time constants available enough that it also modifies. So the average value of capacitance now starts increasing as I increase VGS, and at maximum VGS it shows as if it can follow anything like 1 hertz. If I do it, it will go back to its original value. More details other books. So the idea is I can measure for a given technology a MOS capacitance at high frequencies or low frequencies together individually, otherwise that is what all that my other colleagues in the so called device area, only thing, of course should not say only, major thing they measure is a CV measurement, and keep telling we did great research. This is all that we do, okay, keep measuring CVs. Okay. At the end for the circuit, what I am really looking for, equivalent circuit. I am not interested, as I say, yeah, this theory I did fine, why it satisfied my ego, oh I understood, okay. But for a circuit, how does it matter? It only wants equivalent, put it what you want to equivalent of that. So we figured out in a MOS transistor shown here, just for the sake of, forget about this figure right now, you can write down this expression. There are 3 capacitances of interest at the input side. Which are the 3? One is gate to the bulk, which is called CGB, gate to the bulk, bulk means substrate. There is a capacitance between gate to the source, so we call that as CGS. Now you say from where this is coming, if you see the expressions, this MOS transistor, just a minute before I will come back, you can see from here there is a depletion layer here, so there is a diode sitting here, there is a diode sitting here. Diode has a capacitance and the reverse bias, both are reverse bias anyway. So diodes have capacitances, source to bulk, okay. Which side has a higher capacitance? No, drain side has a larger depletion layer, no? So smaller capacitor, but smaller capacitance have more difficulty than a larger capacitance if they come in parallel or in series, depends how do they come. Now there is a capacitance of from the gate to the bulk, okay, but if there is a channel, bulk is screened, because then there is only small r in series to that, is that correct? So CGB is 0 if there is a channel existing. Once channel exists, the bulk is screened, that means there is no connection with the capacitance, is that clear? So these, otherwise if there is a short channel here, there will be a capacitance here, oxide capacitance and also bulk capacitance. So these are the capacitances associated with. Now what we do here, which is what the trick we are saying, in a MOS transistor, in fact if you see all positions have different capacitances, we will see later. The channel does not have same thicknesses, okay. So the voltages across every point is different, so essentially we are saying we have n capacitance going from source to drain, all in parallel, okay. So what is the model we can do for a circuit? We say lump it out, half this side, and remove them. Distributed something solving is a difficult task, it is like a transmission line theory, RC network solving. Here I say okay, use lump models. So there is the catch word I am using, analog circuit design essentially uses lumped models, is that clear? As all our derivations which we will do later are essentially assuming that lump models are valid. Once you say lump models are not valid, we say this is the highest frequency you can use, because for the design you can only do this much. That frequency we want to know up to where my circuit will function. Okay, you know, at the end I have to find now my analog circuit will function at 1 megahertz, 100 megahertz, gigahertz. Where is that cutoff which I have? Okay, now that frequency is essentially decided by what? Up to which frequency by the device you can have lump model equivalently fitting the experiments. This is the basic understanding we use. So beyond that, not that one cannot solve, but we will have to do something transmission line theories like we do in microwaves, and probably one can solve a more microwave involved problem by using fields, but field theory is not so trivial. Third year people who would have heard it must be knowing about it. It's not very easy to pick up the fundas unless you know very well what is divergence and curl in a better fashion, and to get that field has to be there. So we will say okay, we will use only up to lumped circuits and we will be safe in all our analysis. Is that clear to you? Is that point clear? How do we increase that frequency? Maybe we will see. Can I increase this cutoff to a higher level, how much higher I can go? Can I go to 100 gigahertz? Possibly yes, possibly no. So we will see that. So my issue is that I must know my capacitances, because if you see my earlier circuit, which is that equivalent circuit I drew for you first day, first point, where is that? Maybe, okay. If I have now a capacitor here, a capacitor here and many other capacitances, then I have a problem because circuit has a feedback. Circuit is some input cannot be going beyond certain impedances shown here. That means the limitation of a frequency will appear as soon as I get actual capacitance in the circuit, and that is what I want to know, how much is the maximum frequency I can have, so that I can operate my amplifier, oscillator, whatever circuit I want at those frequencies. Now this capacitances is what we are trying to figure it out, how much are they. Of course what I am showing here can be useful for even the digital course who are taking VLSI design course there, this is same, it does not matter here or there. Okay, so we have three possibilities, CGS, CGD and CGB. Now CGS, which is gate to source capacitance, there are three regions of operation. What is sub Vt? It is phi f is still there but not 0, okay, but assuming right now that inversion is so small, practically we are not assuming as if there, okay. So we say sub Vt capacitance is 0. Which capacitance will, if there is no channel, what is the capacitance say between gate and the bulk? So CGB exists, okay, but CGS and CGD does not exist because there is no inversion at the either ends, okay. So we say CGS is 0, CGD is 0. This additional term which I have shown here is that partial depletion layer which was coming there even at 0 bias is taken care, and this is our oxide capacitance, is that correct? Now if you see the linear, what does that linear, we are not just talk, but in which that VGS minus VT is less than VDS, assume right now that is called linear mode, in which case we can now lump it half oxide capacitance to the source and half to the drain, and then we say there is no CGB because channel exists both, so screened out. However, when the device is active mode or what we are interested in all through theory, which we call saturated mode, we are just, we will come to it soon now. At that time it is a trapezoid of the channel, and therefore we say it is 2/3 area into oxide capacitance. Since the channel is up to corner to this, the bulk is screened, drain there is no charge left there, so this is also screened, so only capacitance available is C. So in general what we do is, for a general purpose irrespective where the device is operating, we add all these capacitors at 0 in a DC case, okay. If that occurs, you can see if you add any term which is very close to Cox, this is 2/3, so maybe 1/3 plus add, so Cox is upper value of that. This also will give upper, sorry this is I think minus sign, you just check. So essentially if I use only Cox, I may be overestimating, that means my frequency actually will go down than what I expected, really may happen, but I am safe, okay. So many a times the first design goes with COX itself, okay fine, thank you very much, okay. Otherwise if you are solving on a computer, how does it matter if the circuit is given all the specifications and all the values, so it will calculate and substitute every voltage whatever is happening and use that capacitance at that point, okay. So in numerical analysis I do not do any assumptions, I say this is the solution, you solve, okay. In the case of analytical I have worry because every time then I will have to remember or add correctly, okay. So I want to make some simpler assumptions, not that I may use this also, but I am just trying to, so many books will say they are using everywhere COX. The reason why they are using is because of the assumption is that it is little overestimation, but fair enough, okay. Okay, let us quickly finish up the device part so that we will actually go on the major issue of our interest. But as I say, why I am showing a device, because I want to show you those parameters which process and design is required, I mean design parameters from where they can be controlled, because that is why I want to know the theory, otherwise for me expression is good enough. Spice maybe there are versions, okay, we will only give you the first version. Why we are doing that? Because there are the problems which we may give will be only simulation problems, okay, and you must run Spice, okay. Essentially Spice solves a small network. What is it solves? I is equal to G times V where all three are matrix, is that correct? That is all that it does. Now these G's could be voltage dependent, current dependent, कुछ भी source हो सकते हैं वहाँ पे, so that non-linearity certainly comes. Larger the parameter, matrix may become bigger, larger circuit may have so many nodes to solve. So the complexity of matrix solving may increase because of the non-linearity terms and because of the larger sizes, is that clear? But basic idea is Kirchhoff law, G into V is I, is that clear? So that is what Spice does. Now what is G? You must know device parameters you must give so that it can calculate dependent sources. So it needs data from the device, it needs data from the connectivity from which node to what node, what component you are putting. Once it knows the circuit, it just does G is equal to V and you can calculate V or I any position, any mesh, okay. That is essentially Spice. What Spice stand for? Spice लाइफ में बहुत होता है, सिमुलेट तो है ही, अभी तो एस वर्ड लगेगा ना, सिमुलेशन प्रोग्राम स्पाइस, आई सी इंटीग्रेटेड सर्किट, ई emphasis, okay. This program was written by Berkeley group headed by Professor Newton, unfortunately he is no more. He was the provost of, not provost, he was the president of Berkeley some time, and his group has written this program SPICE. Now all industries actually working on SPICE, but they have modified model, they have modified few things and then keep telling, oh this is our mind. Thus Mentor Graphic has its own SPICE, some other Spectre नाम देंगे, basic SPICE का ही मारा हुआ है, okay. Reason is if I have a what we used to call a small routine, I may block that routine for anyone else. So I may still run SPICE there. For outsider you say I do not know what program I ran there, I just call from somewhere, run that, okay. So everyone is using SPICE in one way or the other, okay. HSPICE, Synopsys came with some other name, okay, because they say it takes care of both high power and high frequencies, HSPICE, okay, some better models they put. But basic idea is GV is equal to I and nothing more than that, is that clear? So do not get too much worried. And it is best thing to happen because then you can listen music, you can talk people, things will be done by someone else for you, okay. So it is good. Okay, quickly we find out the current, because at the end of the day for a circuit person I want to know, given a voltage on the device, what is the current I am going to get, okay, because that is what my model is asking, what is G, okay. So I say okay, I must find the relationship between currents and voltages. If I get that expression, some way I will convert into a equivalent source, and if I do that my job is over. So I figure out what is the MOS transistor doing. If VGS is greater than VT on an n channel device, VSB is 0, source is 0, and I am applying positive VDS and I am applying positive VGS greater than threshold. Now there can be two possibilities of course, but first we say VGS is large enough, okay, VGS is large enough and VDS is relatively smaller. Please remember, once VGS is greater than, a channel may exist in the substrate. As soon as channel exists, the one shown here, okay, this is source, this is drain. How does it look? This is an N plus area, this is N plus area, this I am applying plus VDS small enough, but and this I am grounding. What does it look like? A semiconductor bar with voltage VDS on one side and ground at the other. So it is like a resistor, a small resistor. Since it is like a resistor, which law I am following? Ohm's law, or drift current only flows, okay. J sigma E is the equation of drift currents. Sigma essentially is conductivity, which is related to resistance, okay. Since Ohm's law is to be followed, now I must know what is R, because if V I know and I want to know I, so I must know V by R. R is what I calculate for this device. This is what all that we do when we solve it. So the first assumption we make, there are three electric fields, or rather two strongly electric fields. Let us say this direction downward is X, across the channel is Y, and along the third dimension, plan dimension, it is a Z, okay. This is the axis I used. So you can see from here, if this is X, there is the electric field downwards, positive VGS, which I call is EX, across oxide. Because there is a current in the channel, there is a voltage, means there is a electric field, this divided by lengths equivalently, not easily, okay. So there is a EY and there is EX. So the first assumption I make, EX is much greater than EY, which is called gradual channel approximation. We can remove that. What is essentially telling that the electrons available in the channel are essentially governed by the gate and no one. Is that clear? ऊपर से ही control है, nowhere else. So gate is controlling the charge. Is that clear? So this essentially says EX is stronger than this. So this controls the charge. Okay, that is what gradual channel approximation is all about. Or to say the inversion charge is, what is charge density is? Capacitance per unit area into voltage. So if you see it, what is the capacitance here? Cox, just at this place. What is the voltage you can see from any point here? I applied a VGS here, okay. Current is flowing in this, electrons are going in this, so current is going in this direction, drain to source. Since this is a resistor, what does that mean? At every point of the channel, that is from y is equal to 0, y is equal up to y is equal to L, there is a voltage drop. What is the net voltage drop at L? VDS, which I applied. But at the source 0, from 0 to VDS there is a voltage drop everywhere. Is that correct? So if I take a channel, let us say this is my channel, and at any point here y, this is my y is equal to 0 and this is my y is equal to L. At any point on the channel, I use an element of the channel dx as such, and then I say okay, if I can calculate the resistance here by rho L by A expression, and then integrate it out across the channel length across the x both sides. I take a piece and I actually integrate on x side and integrate on y side to get the net equivalent average resistance, and I is equal to V by R. That is what I am doing. So I figure out the charge density is VGS, if I apply VGS, minus VT because that is required for inversion, minus Vy because at every point now substrate is equivalently saying at Vy. In normal case of capacitance, substrate was grounded. Now at the lower side of the voltage is potential there. So what is the voltage across the oxide now? VGS minus VT minus Vy multiplied by capacitance per unit area will give me the charge density available of electrons in the channel below. Is that clear? Now this is an approximation. more accurate expressions can be done, but we just see. We also know from the very simple electrostatic law, electromagnetic electrostatic laws, the current in a resistor essentially is q times velocity times the width. The width comes because as if you have a number of such channels and you have to add all of them, so multiply by w, okay, assuming that is constant, okay. That means this w is uniform throughout. So if I do that, I have a qvw is the, this is charge per unit area, please remember. What is the velocity there? Mobility times the electric field, is that correct? I have a drain current which is charge density, electron charge density into velocity, and velocity is essentially mu Ey into width of the channel. Better expressions can be derived, but just to take from this. So if you now know IDS, if I know my Qn which is here, I assume now mu is constant, but in reality mu is also not constant. So we have to take care of mu variations. Ey, how much is Ey? 0 to L, it goes from 0 to VDS. How much is the voltage across channel? As the length goes from 0 to L, voltage goes from 0 to VDD or VDS, is that correct? So if I integrate these two terms which I am going to, then I will get net average I is equal to IDS equal to average resistance multiply equal to voltage across that. This is what I do. The second assumption which I make, which I said V is equal to mu E is always available, but that is not true, because if E increases too much the velocity starts becoming constant. So right now my assumption is V is not reaching Vsat, which may actually, okay. So there is another assumption I made. First assumption, what did I made? Ex is much stronger than Ey. Second I made assumption velocity is still not saturated, which what does, when this can occur? What is electric field? Is VDS divided by length. So when Ey will be smaller, either the VDS is smaller or L is larger. Larger channel link devices called long channel devices. So in a long channel devices this assumption is good enough, we say velocity does not saturate. What is the new problem will now come? As you go for smaller and smaller dimensions, the velocity will become saturated day one, okay, and that is our worrisome part as we come to the models. Third assumption I made, which is also an assumption, that net current in the channel is essentially drift current. That means that is the only current I have. Which is the other possible current in a semiconductor? Diffusion current. But I say there is no diffusion current. There is no gradient, though there is, but that current is say million times smaller than the other. So I say there is nothing there. So the third assumption say only drift current occurs. This is also an assumption. In real devices, if you are doing a device simulation projects or something, you can get rid of all such assumptions and get exact values. But to your great surprise you will find it does not give the exact experimental result in spite of great modeling. Then finally what you do, you try to fit some parameters which fits into experiment. Once you start fitting, then whole physics is lost, okay. So physics and fitting do not go together, but what do I do it? I still want to retain my physics, so I add constants to it, maybe less than 1 or exponential some term which is say constant, we say. So it is called fit constant, fit functions. So keep physics with some fit functions, okay, weightage, and then you say, oh, it fitted my physics also, it is good, you are just trying to fool yourself by why choose the same physics. You could have written alpha 0 plus alpha 1x plus alpha 2x polynomial, 100 के बाद कुछ ना कुछ तो फिट हो जाएगा, अल्फा कुछ भी एडजस्ट हो जाएंगे, ऐसा नहीं है. वो फिजिक्स रखना, उसको कांस्टेंट वेरी करना. स्पाइस व्हाट डज इट डज इन मॉडल, as you scale down technologies it changes its constants, fitting functions, because experimental given technology is known to you, okay. So you try to come closer to it and you say, look, I have got exact physics and exact fits, okay. This is game all device simulation people including me play, okay. As I say, I already said new structures and new smaller devices, diffusion current may not be as small, though we do tricks so that it becomes smaller. There is another assumption I make. We assume, as I said, mu is constant, but in real life mobility varies with electric fields. Okay, so even mobility is not very much constant. It's a function of y, it's a function of x also. Okay, x it comes from what we call interface state density. Right now we will not go into it. So mu is not even a constant. But all these assumptions when you make and get IDS, VDS characteristics, what do we call textbook model, which probably, and then the actual model what will be, give K1, K2 something, so that it fits to the reality. Okay, so I say look, this expression I am still using now. That is the game all SPICE models people do, okay, including us. So if I now substitute using first order assumptions, I write Ey is dV by dy, electric field is slope of voltage, okay, Vy. I substitute in this expression which I wrote, I write IDS dy is W mu Cox Vgs minus Vt minus Vy into dV by, y changes from where 0 to L, Vy varies from at source 0 voltage, at drain Vds, I integrate from 0 to L to 0 to Vds and I get this expression. IDS is mu Cox W by L bracketed Vgs minus Vt Vds minus half Vds square. This is the simple integral of this. What is it trying to say? Mu is constant, that is why it has come out before integral. I also assumed, as I say, Vt constant, which may not be, Vt is a constant value. So I just in differential integral I did not use that, I said Vt is constant. In real life even that may not be constant. Okay. Now this in my analysis, analytical analysis, I use mu Cox term, I call it beta dash, is that correct? And this beta dash into W by L I call beta, which is like telling bipolar transistor used to have a gain factor, so this is equivalent of a gain factor. Okay, so I may use in my final expressions betas, beta dash is mu Cox and beta is beta dash into W by L. This is my writing, it is not necessary, you can keep writing mu Cox W by L everywhere and fair enough. This is just to reduce the size of the expressions I write, is that okay? I repeat, how did I do it? I wrote QVW as my current, I know V is mu V, so and E I had substituted dV by dy, then I figure it out, I can integrate this from 0 to length because that is what the resistance blocks are. Okay, so I just summed it them all, and once I sum them all I get this relationship. Now the trick, worrisome part is now after you write down this expression, you will find if I really plot this IDS versus VDS characteristics, then I am some funny characteristics I suddenly see. Now the fun starts here, if I plot this expression IDS, this expression, okay, for all values of VDS, okay, I figure out initially, you can see from here, if VDS is smaller initially, this term is small and IDS is proportional to VDS. If VDS is smaller, please remember half VDS square term is smaller, neglected. So IDS is beta times VGS minus VT, and if VGS is fixed by me, IDS is proportional to VDS, that is why it is called linear mode. IDS is proportional to VDS. What is the condition? VGS minus VT is much larger compared to VDS and therefore this term is neglected. However, if this assumption does not go and I keep increasing VDS, that expression now says as VDS starts increasing, the current starts decreasing because minus half VDS square term start increasing, is that correct? And at some this VDS, actually IDS is 0, it is going down. So it looks parabola because that expression is half square, I mean parabolic, so it shows a parabola. But in real life no one has seen that beyond certain voltage current suddenly dropping down, that means current remains constant, people have seen that expressions, okay, characteristics. So what has happened? So we say okay, in real life if there is something has to happen like this, this point I must know where this can start. So I said okay, what is the maximum value up to which current is still one directional. So I differentiate this, equate it to 0, and I get VDS equal to VGS minus VT at the point beyond which the current will fall. So there must be something related to this point, VGS minus VT equal to VDS is the issue. At this point onwards something else is happening. Certainly linearity is not there and no other term going higher negative, so that current goes down. Now what is beyond then this value? Beyond this VGS minus VT, if I further increase VD, I do not get this. So the theory is something which is what device is very interesting about. Is that plan clear? In reality I never see going down, but the expression shows it should go down, okay, it does not. So what could have happened at this voltage beyond? Now this voltage is very crucial, as if you see when the threshold occurs in a capacitor, if you see you have a capacitor, this is your metal, this is your substrate. What is happening? Vg minus Vs is the voltage across oxide. This should be greater than Vt to have inversion or plus or minus whatever. If it is plus, then I want inversion to occur here. Is that clear? This is how we defined it. Essentially now saying if Vg minus Vs is less than Vt, there is no channel. Is that correct? That is what capacitor theory says. So look at this transistor. If you increase VDS beyond VGS minus VT, or at that point when VGS minus VT is equal to VDS, what does this value essentially saying? This is VGS, this is VDS, is that correct? This is 0. So all voltages are measured from 0, VGS as well as VDS. So VG minus VD is nothing but VGS minus VDS, is that correct? Because source is grounded. Vg minus Vd is same as Vgs minus Vds. So if I use this expression Vgs minus Vds, this is at this point is occurring, is that correct? If now Vds increases beyond this point, what will happen? This quantity will become minus, so there is no inversion possible. So just beyond this point Vgs minus Vt is equal to Vds, beyond this value Vds increase, there is no inversion at that end. So what you see here, there is no inversion when Vds reaches Vgs minus Vt value. Please remember source is grounded, is that clear? Gate voltage you are in fixed very high but higher than Vt. So at the source there always will be channel, because Vgs is always greater than Vt, that is we started with. So source will have a channel all through, but at the drain end at the point when Vds becomes Vgs minus Vt, channel is not existing at that point, it is called pinch off. So channel is pinched off. But since Vy is varying along this point, so Vgs minus Vy is decreasing along this line, which means the number of electron density available in the channel will keep on changing as you move from source to drain. Larger here because the maximum potential is given by you Vg minus 0, is that clear? In between smaller, at the end it may become 0, okay, which essentially means the channel thickness will be maximum at the source and will keep on decreasing towards drain end. Normal in case of channel existing throughout, even then it will be something called trapezoidal, sorry, it is a trapezoid. But if you further increase, it may actually pinch at the other end and it may become triangular. So initial trapezoidal channel will become then triangular, is that correct? This point we call device now enters saturation. At this point, that means Vds greater than Vgs minus Vt, device is entering saturation. So what does that mean? In the case of bipolar, I do not know how many of you still recollect, when I say I see VC characteristics and I say device is in saturation mode, what does that means? Actually VC is very small in a saturation. The reason we say okay both junctions are forward biased, okay, IC becomes maximum. So we say this is the saturation. In MOSFET that is called linear region, the current when it becomes constant saturated we say you are in saturation, that is the name change from there. So now if you declare this that pinch occur here, I further increase VDS, what will happen? Current is increasing. So this point may actually shift from the drain end to this, because now VGS minus Vy itself may be small enough to pinch that channel, that point, which what does that mean? You may have this pinch off point shifting from drain towards source as I increase VDS beyond this value, is that correct? Now the question in physics was that if you have a channel which is pinched here, this is my source, this is my drain, okay, and I am applying a VDS which is greater than VGS minus VT. Electrons were moving in the resistor, but what is here? The depletion there is no free carriers there. So why carriers should go? There is no current, current should have gone down 0 immediately, it still did not go. This is essentially saying this is a depletion layer, this is something like this, it is a large depletion layer. There is in this depletion layer you have a large electric field, the direction is positive to negative. This large electric field, whichever carriers are coming from here are sucked by this electric field and brought down to the drain side. This is essentially how bipolar transistor works. As the carriers reach base collector junction, the electric field there is so high it collects, okay, same procedure. Is that clear? Otherwise the current should have gone to 0 suddenly, it did not, it actually sucked out. So larger the field here, the current, but how much is the current? Whatever this resistor can give you, only that much carriers can be picked up. That is decided by your VGS, VDS values, you already decided. But once it reaches there, at that point whatever carriers are available to me, I will just pull it up. Okay, is that point clear? This is the reverse bias PN junction theory. Whatever is available will fall down. How much I am not sure, whatever you say because that slope is so high, electric field is high, it will fall down, okay. This is the theory behind the pinch off ahead. If I do this and if I substitute those VGS minus VT, I call this value saturation, at which at a given VG value VGS minus VT reaches VDS, that value is called VD sat, okay, it saturates. Now why currents become constant? That is still not answered by us. The current is becoming constant because as you increase VDS, the net, this triangular part whatever it is, the charge density is only governed by VGS, so that is not changing, is that correct? So the available carriers are not really changing for you, because as I said gradual channel जितने ऊपर से उतने ही मिलेंगे, आपने ऐसा किया या ऐसा किया carriers उतने ही थे, which essentially current cannot now change because whatever has happened is remained there. So current becomes constant or saturated. So it is essentially now trying to tell the following, it is telling me if I plot a IDS versus VGS character, what is this curve called? IDS is the output current, VGS is the input voltage, transfer characteristics. This is drain, this is this. For N channel this is direction. So input to output relationship is called transfer. So I figure out as long as VGS is small, less than VT, How much is the current? It is not 0, I said at VGS equal to 0 it is 0 because there is nothing there. But as soon as you go beyond 0 till Vt, what is the situation? We are still in inversion but small inversion, is that correct? Vt was defined as 2 phi f value because it started at phi f itself, okay. This region is called sub-threshold region. There is a current going on, okay, there is a current going on and it is exponential, we will see later. But at Vt, which is what you say, current then start going heavily, okay, and as it starts, VGS starts increasing, VGS minus Vt takes over. In this case VDS is required, why? Though VGS minus Vt should be much larger than VDS, VDS is still required, otherwise current cannot go. So VDS is kept in millivolts, tens of millivolt to hundreds of millivolt, and VGS varies from 0 to VDT. So if you see, the current starts shooting heavily VGS minus Vt times. Now this is the called transfer characteristics. If I do the output characteristics, so what do output characteristics is? It's called IDS against VDS. Please take it, sorry, I just draw, I will show you. The potential between this is VDS, which is essentially for output in most cases, okay. So if I plot IDS versus VDS at different VGS values, I get for a smaller VGS which is less than Vt, a very little IDS, which is this current essentially flowing. Two currents it is flowing. Which are the two currents I have flowing here? One is sub-threshold. What is the other current in a transistor can flow? Reverse saturation current of the two diodes, whichever is smaller, one of them will flow, is that correct? That reverse saturation current plus sub-threshold current is essentially small current. This small word is not really small because in newer technologies that is my issue. I said you in a some day that 32 nanometer down the off current may be more than the on current. That is why I use mobile constantly, so that power drain come home. So that is exactly the reason. So off current shown here is very small. So analog people are therefore not very happy to go to 32 nanometers or some 0 nanometers kind, okay, we are worried actually. Beyond this value, initially current rises linearly, and for given VGS minus Vt equal to VDS, smaller VGS, this point will be faster, VGS minus equal Vg is small, so VGS minus Vt is small, so smaller VDS it becomes saturated. Larger the VGS, saturation points goes above and above and different characteristics are seen. The only problem which I see here is something worrisome, and that may be interesting as well. I just now made a theory which is said current becomes constant independent of VDS, that is what I say, whatever available I push, okay. But in real life by monitor I see on all such characteristics there is a slope. What does that mean? IDS is, earlier I said in saturation it is independent of VDS, but it seems it is not independent of VDS, marginally varying but varying. And another feature which we will see later, of course not shown properly, occurs if these slopes I actually extend it in the minus VDS time, they all curves meet at one voltage, okay, and that voltage we call is Arley voltage, which is taken from Arley effect in BJTs, okay. There is no Arley effect here, but the voltage is still given a name, Arley voltage. There IC VC characteristics at different IB, if you extend down at one value of all of them meet, which we call as where the base gets punched, okay. So we say that is Arley voltage. Now here also that effect is there. Now that Arley voltage has some interesting value because then I can calculate my R0 if I am given a Arley voltage. So that is the why I said Arley voltage. Now I want to know if I have to represent this few minutes, these characteristics as an expression first, and then once I know expression I can calculate from expression what? If I know IDS function of VGS and VDS, I can differentiate with respect to VGS. so I get Gm, I differentiate with VDS, so I get my R0, okay. So I must get a relationship first between IDS and which I first derived, but now let us see what can happen. If VGS minus VT, which I defined as, please take it, VGS minus VT I defined as, some books defined as VGT, some books like Boyce and Laker's book, Baker, Boyce and Lee's book define excess, and I define over voltage, my definition, okay. Why so many years I am talking, so I do both. Why I say over and above VT, how much, okay, which makes translate go. Of course this is something taken from one of my old colleagues from Stanford, so I just use his this, so VOV. So in a book, if you are having a different book, same names will be I am using VOV, they may use VX or they may use VGT, whichever name they are giving. Please remember they are same, what is it, VGS minus VT, is that correct? Now we say if VOV is larger than, condition is VDS, that is VDS is small, that means channel exists throughout, device is in non-saturation, it is not saturated, is that correct? Device is in non-saturation, the current can be given as beta, which is mu C of W by L, VOV times VDS minus half VDS square, is that correct? VGS minus VT is replaced by VOV, okay. This is what mode? When the channel exists throughout, and that condition can only occur when VGS minus VT is larger than VDS. Once VGS minus VT reaches VDS, we know it enters saturation. So prior to this, that means channel exists throughout, okay. Is that okay? So in a non-saturated mode, the current is, and why I say it was linear, because if VDS is smaller, IDS shows linear relationship with, so for a smaller VDS you are more linear. As you reach towards saturation, VDS is not very small, so you see curve slope changing, okay. You can see from here, as you reach here the slope changes, okay, and that is the reason it changes. So what is the model I am really doing? It is called two region model. One I will say like this, the other is like this, okay. एक ये रीजन, एक ये रीजन, बीच का क्या करेंगे, whenever there is an issue, two models at that point must have same values, okay, because that is the fixed value. So at the knee point both models should give me same values, this is the knee value I will say. If that I get it, I say fine, two regions it fits, now that word is fit, okay, it fits, and then I use two expressions independently as if I do not know what the other is doing, okay. That is all modeling people do, okay. Device people do not do it, they do not like that, okay. If now you say VOV is larger than VDS and IDS is proportional to VDS, what is it looks like? You can see from this curve again, on this region, you know, slopes are different, is that clear? At different VGS slopes are different. That means it is equivalently saying it is a variable resistor. As long as you are non-saturated at any VGS, you have a different resistors, is that correct? Linear is with a different R. So a device acts like a variable resistors in non-saturation, as straight as that. However, if I now increase VDS further, I say pinch off may occur at VOV equal to VDS, or VOV becomes smaller, it may further get saturated heavily. Then one can see from here that expression, which I will just show you, I will just repeat again. If VOV is equal to VDS, my expression writes IDS is equal to beta VOV into VOV minus half VOV square. At this point, this is the expression, which is half beta VOV square. Is that correct? Half beta VOV square. So what does this, does it have any relationship with VDS? No, as of now. We will increase that. So what is it acting like? IDS is independent of VDS. What does it look like? Output current source. So a transistor in saturation acts like a which current source? Voltage controlled current source, VCCS. Okay, it acts like a VCCS. Okay, so सब लोगों को अच्छा लगता है यदि ग्राफिकल कुछ दिखाया जाए. तो एक छोटा ग्राफ है VDS versus VGS. I am shown here. If VGS is less than VT and VOV is, you are less than, VDS is less than VOV, this region is subthreshold. Anything below VOV, VGS minus VT is greater than VDS, and VDS is smaller than VGS minus VT, you are in non-saturation, which means you have a variable resistor, and VOV is smaller than VDS and VGS is whatever it is for this value, you are in saturation, which acts like a current source. Is that clear to you? This is what equivalent of a MOS. So now I know if I see a MOS transistor, depending on the voltages I am using in my circuit, I can replace the device by equivalent current source or equivalent resistor depending on the way I am working at. If I force the device to always remain in saturation, then what will happen? The MOS transistor will always behave like a current source. That is exactly analog region. When the device VO-VI characteristics show slopes, both devices of P channel N channel are in saturation. Therefore, we say the MOS transistor analog is always like a current source, but at the edges it does not. So, signal if goes beyond so called non-linearities may set in. Okay. Finally, last expression for the day and we will stop here. In saturation, in real life I say there are slopes. IDS beyond saturation point also keep increasing very little way, I mean the slope is very low there. Now if I see it is a very slow lobe, I can fit it this, okay, I fit the curve and I figured out this is my normal saturation current, I multiplied by lambda VDS, 1 plus lambda VDS, where lambda is called saturation parameter, okay, which we can derive of course, is equal to what we call lambda dash by L, where lambda dash is equal to 2 upon q substrate under root. We can derive all the theory of that. When the device is having a flat, this from this characteristic, can you say if it is very flat, what does that mean? Lambda is 0, flat. As lambda increases, 1 plus lambda VDS factor will start increasing, the slope will start building. Is that clear to you? So in a technology, it's more, you can see it is substrate dependent. It also is depending inversely proportional to length. So if I want smaller lambda, what should I do? You can see I want smaller lambda, so I should have larger substrate concentration, but what does it will do? Increase Vt. So if I increase Vt, what will happen? My net current will go down, okay, and as I later will say, the GM will go down, okay. However, the other possibilities I use longer length devices. So is that now clear that in normal good device, I want saturation to be very good, okay. So what should I use device lengths? Larger than normal technology node. For example, you are working on 90 nanometers, you should not use channel length everywhere 90 nano, use it 180, 270 something, 2 times, 3 times. So the analog functions will give better because of lambda will become smaller. Is that clear to you? This is the crux of all analog design, how much channel lengths you should use. Longer channel devices therefore will give you better analog performance any day. Is that clear to you? That is why 0.25, 0.35 micron technologies will give you better analog performance, and 65 nanometer, 45 nanometer will start killing you. Okay. How do I get rid of both? That is the design part.